Most engineering schools get one thing backwards. They teach you that engineering starts with complex calculations, but that's not the reality of the job. Even the question that you ask sometimes has answers baked into it. The real heart of engineering, the skill that actually solves problems and creates value, is something else entirely. The heart of engineering isn't calculations of formulas, it's problem solving. I'm Brogan Pratt, and as a robotics and design educator for over a decade, I've seen that some of the best engineers are not human calculators. They're expert problem solvers. So if engineering doesn't start with a calculator and with formulas, where exactly do you start? You start by asking questions. And one of the biggest problems in engineering is trying to find a solution before you fully understand what the problem is. So let's take an example here. A client comes up to you and they say, hey, I've got a machine here, and the machine is sitting on top of a bracket. And this bracket that we have right now keeps on breaking. I need a stronger bracket. Well, the novice engineer might start saying, all right, well, let's start calculating how much is the load on this total system and how much extra support am I going to need for this bracket to be able to hold up the load of this machine. And you're going to start calculating out material strengths, how much actual thickness do I need? What grade of steel should I be using? Is steel the right material for this bracket? But that's heading down the wrong track from the start. A better engineer is going to ask, well, why do you need a new bracket? Well, obviously the client's going to say, well, yeah, because the old one broke. It's no good anymore. So then you'll ask, well, how did it break? I don't know. It snapped after a few months when we were using the machine on this. Okay, well, what's the machine do? And maybe they say, well, it's a rock tumble machine. And what it does is it is deburring all of our parts. So that should automatically tell you that, oh, this isn't actually a load problem. This is actually a vibration problem. This machine is going to shake a lot during its use. In this case, the problem was never strength. The problem was that it's fatigued, or you got material fatigue from all those vibration forces going through. And a stronger, more rigid bracket might even break faster because of all these vibration sources. So a different solution for this one might actually be designing a damper that goes underneath the machine so that you don't have to have all those vibration forces facing itself on top of that bracket anymore, so that those dampers reduce a lot of those vibration forces. Another solution might be designing your bracket out of an entire material completely so that it doesn't have to get forced by, or doesn't have to be affected by all those vibration forces. So the calculation you need to do is completely changed because you define the real problem first. And this leads to identifying your constraints. What budget do you need, what materials you need, what size, what's your timeline, and those define the solution, or those that define that box, those key design constraints that your solution has to fit inside. So after asking why and really boiling down to what you think that main problem is, now you can actually start iterating on some of those solutions. Sometimes, even the question you ask can change your answer. So for instance, you have a lawn with a lot of grass on it, and you ask, what's the best lawnmower I can buy? Question you just asked already has answers baked in. It's assuming you have to take a lawnmower to come along and cut the grass off. A better question might be, because the real answer you're trying to think is, how can I make the grass shorter? That's a completely different question. Now you start getting the ideas of, well, could I put in a tree so that it can shade on top of my grass area so that my grass doesn't grow as fast? Is there some sort of chemical retardant I can use so the grass doesn't grow as quickly? Could I replace the grass instead with clover? Would that be a possibility? Could I use moss? What are other ways that I could make my grass shorter without having to use a lawnmower? So even the question that you ask sometimes has answers baked into it. So now that you've better designed your problem or better understand your problem, now you can actually start designing solutions that work. This is where you use your cheap materials to get your rapid prototyping out. Use your cardboard, use your scrap wood, use your hot glue, use your paper clips, whatever can get that concept out. So for example, let's say you need to build a robot that's capable of picking up a circle from the ground. You don't start by saying, okay, well, how heavy is the circle? How much motor torque am I going to need to be able to pick these things up? You start to think, what are some ways that I could pick these things up off the ground? So you head over your sketchbook and you think, all right, what if I use some sort of robotic claw or gripper to pick these things up? What if I use some sort of scoop or bucket and I drove into that piece? What if I used some sort of rapidly spinning wheel that rotates around to be able to kick these objects in? What if I were to change these rotations so that rather than picking up from like so, I almost use a vacuum and I have two of those wheels and they rotate to pick the object up like this instead. And then once you've got your ideas out, now you start coming up with a bunch of different ways that you could actually build these. Build them out of cardboard, build them quick, grab out a hand drill to simulate a motor so you don't even have to bother programming it to be able to simulate those wheels spinning around. And perhaps you find out that the claw works, but it's a little bit slow. The scoop has too fat of a lip, so you trim that down and it works, but it's just as slow as the claw. And then you find that that intake wheel works, but presently it's a little bit too aggressive, but it is really quick at picking that up. So now you can help find that best concept really quick and work off from there. The goal here is that you're trying to fail fast and fail forward and do it quite quickly because you want to be able to get that best conceptual space to be able to find that best path forward. So now that you've defined that problem and you've done some rapid prototyping to figure out which concepts really start to hold some salt, now's the time to bring in some of that calculation. And calculation really here serves two main purposes. The first one is validation. You have to prove that the design is safe and it works underneath its intended purposes. Can it hold up to the stress that you need? Do you need to do some sort of stress analysis to be able to figure out what sort of steel thickness you need? Does it fit within your budget design constraints? This is your reality check from that quick design. And second, we talk about optimization. Your design works, but it's pretty rough. And it could definitely be better than where you're currently sitting. Can we make it lighter? Can we remove materials that aren't facing levels of stress right now? Can we use a smaller or cheaper motor so that calculation for optimization allows you to squeeze out extra performance for a little bit less budget and really allows you to refine your concept and your proof of design. So all those calculations and formulas aren't really that starting point, but it's a great place to finish off that good idea that you started with. So the recap, that engineering flow is really defining the problem, creating a concept, then doing some calculation, not the other way around. And sometimes school can teach you a lot of tools, but it has a bad time teaching you when to use the right tool at the right time. And really, as an engineer, one of the most important things that you can refine is when to ask why. So if you're still a student, you've got a homework problem and it's telling you to solve for X, you might want to think about, take a few seconds, take a step back and think, what might be a real-world application of solving for this X? Why might I need to be solving this answer? What real-world scenario would I be using this calculation for? That can really help ingrain your thoughts a little more as you study further engineering. Because the goal with engineering is always to provide meaningful and incremental improvement. And that doesn't always start with numbers. It starts with deep thinking and some creativity. If you've got an example of when you thought you had understood the problem, but were wildly out, let me know in the comments down below. Otherwise, I hope you enjoyed this talk today, and best of luck out there on your next project.